Hi, my name is Christian Ramos, and this is my Physics 2 Lab 4. So, table of contents, we're going to have an introduction. We're going to do the first part, the second part, the third part of the experiment, and then we're going to have a discussion and then a conclusion. So, the introduction, so what's the purpose of this lab? So, we're using the conservation of energy to predict the behavior of cellular circuits, then modeling that behavior using an online software, and measuring those values of current and potential difference. And so, the principles we're using, so we're using Kirchhoff's loop rule, where the sum of all the voltage is equal to 0 around a full loop. The node rule, which is the current entering is equal to current exiting. Ohm's law equals V equals IR, which is voltage is equal to current times resistance. And then we're using resistors in series and parallel, and then the conservation of energy and charge. So in the first part of the experiment, we just made a simple circuit with some resistors, some ammeters to measure the current. So our prediction is that current 1 is equal to current 2 at 0.02 amps, and that's because the total resistance is 100 ohms plus 47 ohms equals 147 ohms, and then we predict the current using I equals V over R, which is 3 volts, which is the voltage over 147 ohms, is equal to 0.0204 amps. And in the actuality, it was 0.02 amps during a closed circuit. And then we used the voltmeter, and with this voltmeter, it was equal, the voltage potential difference was equal to 3 volts. And then the current is equal to 0 amps just because it's an open circuit, as you can see on the bottom picture there. It's not a full loop, so there's no current flowing through the circuit. So in the first part of the experiment, the very top is what we did originally, and then we have um, then we reconnected the circuit and we read the voltage at various points with Kirchhoff's rule is equal to the summation of all potential differences is equal to 0. And as you can see on the far right on the chart, we have a voltage of 3 from B to A, negative 0.96 from D to C, and then from F to E, we have negative 2.04. And then when you add all those up, that is equal to 0 volts. So this does follow the loop rule to where the potential difference round trip is equal to 0 volts and the current is equal to 0.12 amps. So in the second part of the experiment, we have a bulb and a capacitor in series. So at first we're going to plug it in and the bulb lights up and then it slowly dims as the capacitor is charged. And then the current decreases throughout the circuit. So it starts at its max and then it slowly decreases until it gets to 0. And then we take the battery out and reconnect everything. And then the capacitor serves as the initial point of the charge. And the same thing happens again. The bulb lights up and then it slowly dims and the current is increased to its max and then it's slowly decreased after that. So then using a voltmeter, this is part 3 of the experiment, I measured the change in potential difference over time and then graph the natural log of potential difference over the initial potential difference to find the RC values. So as you can see, we have our time, our potential difference, and then natural log of potential difference over initial potential difference on the chart on the right. And then there's graph, it's a linearly downward slope. So in theory, our RC is going to be resistance times capacitance, which is the resistance of the light bulb times the capacitance of the capacitor, and that's 30 times 0.2, which is equal to 6 seconds. And then the actual RC is equal to -1 over the slope of the voltage versus time graph, and that is -1 over negative 0.1673, which is equal to 5.977 seconds. So very, very close, almost equal there. So some potential errors that might have been during the timing. There was a delay when I was timing some things from when it was fully connected to the circuit. I connected it all and then started the stopwatch. There's a little bit of delay there just because I'm human and I can't do two things at once. Then what if you were doing the lab in real life and used an actual ammeter instead of the ideal simulated one? What's the difference between a real one and the simulated one? How it affected it? The current would have decreased slightly just because of the resistance of a real ammeter. In the online lab, it didn't have that, but in real life, it would have a resistance. And then what if we were doing this lab in real life and use a real battery and to charge a real capacitor with no resistor in the circuit? How quickly would it charge in our ideal online model versus in real life? Our capacitor would charge immediately due to no resistance in the online model, but in real life, there would be a little bit of resistance from the wire, so it would not charge immediately. So, a couple points to conclude. One, in order to have accurate values, the wires and ammeters in the circuit must be a minimal resistance. So this is why our online model works really well. And then two, current I, and then potential difference, voltage V, are different points in the circuit, at different points in the circuit are time dependent and they decrease exponentially with time.